I wanted to come back to to a couple of points that, maybe these are semantic things, but, we all get hung up on some words, right? I mean, I feel that simulations are the only test for theories, hypotheses, and models in cosmology. They're not crucial tests. So, when talking about what is distinctive between experiments and simulations, I mean, I think these are the only tests that we have. So there's not a class of crucial and non-crucial, essential and inessential tests, but this is the only game in town.
I think
so that's different. That's something that differentiates.
Well, I should clarify that. I think what was meant there would be trying to figure out how much work's being done by the observations as opposed to the simulations.
I see.
I think that's what's at issue there, right? So, do you think it's really the observations ultimately that make the crucial difference in adjudicating? As opposed to the. So, I was just wondering how much of a role is it more than in other cases? Maybe because of this astrophysics phase. There's something weird going on there, which makes the simulations play an extra role that they don't maybe play when you're just doing like some more mundane simulations like planetary motion or something. I don't know. I mean, that's what I was trying to get at there. But.
No, I think it is true that the astrophysics adds a level of complexity that makes them the only way forward and privileged compared to, well, to have better status. I won't say privileged entirely, but better status. Also, I think they are not merely tools for calculating. I think, again, they are the only calculational structures available. There is no way that, even if our brains evolved, that somebody could write out an equation, one equation that will encapsulate the behavior of this many-body system. So it's not, I think it's the only tool. It's not tractable. It's not analytically tractable.
Oh, sure. I guess what I was trying to get at there was, again, compared to something like Navier-Stokes with fluid flow. I don't know, I'm not an expert on the history of either of these things, but it seems to me that in that case, there wasn't the kind of really deep feedback between simulation, observation, more simulation in the process of building the model, right? Well, back then, people weren't doing simulations of Navier-Stokes anyways when they came up with the models, right?
Right, but I mean, the Navier-Stokes is a very interesting example because there are instabilities. So there are these problems of fluid flows where when you solve an equation, you reduce it to one dimension and you solve it. And you can get a perfectly, a solution that sort of works in the mean. But in reality, we live in a three-dimensional universe. It turns out when you actually can do the computation in 3 dimensions, which you can do analytically, you find a whole host of instabilities, of new instabilities that are actually observed on very small scales that in a system where you're making measurements, but the one-dimensional calculation did not even predict them. So or a suppression of some instabilities and turbulence. So that's an interesting example. So computational work has actually transformed the interpretation of observational data for fluid flows, for example. Because there's a whole host of instabilities that show up in 2 dimensions and are suppressed in 3 dimensions and actually show up in 3 dimensions and not in 1 dimension, etc., etc.
So maybe there isn't that much of a disanalogy. So I was just trying to figure out is there a special role that these n-body simulations are playing in the sort of, as the models get constructed, in the model formation process, and not just the testing process.
Right, and I think...
As opposed to, say, older models, like planetary motion model. It doesn't seem like simulation had much to do with the formulation of the planetary motion models, say the Newtonian model, right? I mean, so there seems to be a difference there.
Yeah.
I'm not sure if it's an important epistemic difference, but it seems to be a difference.
So I guess the one other, so I've read Eric's paper as well, it's very interesting. What I don't understand there is this, what is the need for the distinction between an object system, target system? What does that buy you? What does that separation actually buy you?
Well, it's supposed to buy you the idea that often when you do experiments, you're interested in more than just the thing that you're playing with. You're interested
in a general phenomenon.
I take it, right, a lot of what drives your n-body simulations is some understanding of gravity that doesn't come from our having directly investigated the galaxies that you're simulating. It comes mostly from having played with the pendulum and having looked at the planets around in our solar system, and then having tried to make that Lorentz invariant or something like that, right? So I take it that the idea is that often when we do experiments, it's not the thing that we're playing with that we're interested in learning about. We're interested in learning about some wider class of target systems.
Also, you wanted to differentiate
right. And so then the idea was to think, once we take that seriously, And once we take seriously that sometimes, and this is I think some stuff comes out of stuff in philosophy of experiment in the last 20 or 30 years, right? That if you think about when people do experiments and they're trying to figure out at what point do they count the experiment as having been successful rather than having been confounded by various kinds of errors or whatever, it's not so easy to cleanly divide what am I learning about this from what am I trying to learn about broader classes of systems, arguments about whether the experiment has been successful or has failed or has been confounded or whatever. Really, you have to take quite seriously that it's not, it's not so simple to say, first I'm learning about this, that's the experiment, then that's over, then I'm making inferences about other things. I think experimental practice shows us that, in fact, when we're trying to do experiments, we're simultaneously trying to learn about broad classes of systems and play with something locally. And I think once we take that seriously, it's not so easy to say the difference between simulations and experiments is, experiments, we're experimenting on the thing we're interested in. Simulations, we're experimenting on models and then just figuring out what's contained in that model. And both of them have complicated mixtures of nature telling us things and our background knowledge being involved. And I think once we take all those complications seriously, it's not so easy to say the kinds of things that people are trying to say or not easy to say.
I guess one other point I want to mention is that, of course, underlying all of this is the assumption that Newton's laws are going to work on these scales. So another very active field of research at the moment is modifying gravity theories. They're called FFR theories. And there are people working on trying to see if we had an alternative formulation, then can we actually move that forward and set it up in the framework where we can actually temporarily solve it as a function of time. Hasn't been done yet, but people are working on thinking about that. That if Newton's laws really are not valid on these scales, on very large scales, because we don't have any tests. Nothing beyond, and Einstein's laws as well. So Einstein's formulations of GR, both the classical and Einstein's extension. I mean, if neither of those work, then what? And so there are people who are now working out theories that will mimic what we see, and trying to see what are the restrictions on such a theory. Like how different can they be in order to have the same observational predictions at late times.
This actually connects to what Eric just said, and it goes back to some of my own puzzlement about the uniqueness problem. So I'm going to say a word in favor of the uniqueness problem. Maybe I can be corrected on that. What you learn from doing a single experiment, from what you learn observationally, is what happens in the here and now. But you're very rarely interested in just what happens in the here and now. And indeed, the distinction between an error in the experiment and a successful experiment depends on what you're going to use this experiment to give you information about. So you have some background class of systems that you want to use this experiment as a representative for. And we know how that works in experimentation. Sometimes it's a bit seat of the pants, but you need repeatability. You need to know how to generalize across a class of cases, actual and counterfactual. And that separation of the general and the specific is something that one gets with experiment and what a theory brings in. And I think part of the problem, at least in my own mind, is looking at a single history and trying to extract information from that, the kind of information that will both give you allow you to make predictions, and also make predictions across kinds of cases that we don't actually observe, that we haven't actually observed, is that there's no basis for that separation of the general and the specific. And so you pointed to historical explanation, this problem in describing history, but history is not about laws. I mean, they do make predictions, but I think there are epistemological problems there.
I don't know. I'm not a Hempelian, but I would say that historical events do fall under laws. Under certain descriptions.
And to the extent that they do allow predictions.
Right.
To the extent that they're highly dependent on specific particularities, they don't generalize. Historical description is notoriously bad at delivering robust predictions. For that reason, I think.
Well, I think she's articulated what I would have loved to say.
So I think one of the closest